Good morning, E&M crew. Today, I decided we would go over a problem that I think that if you looked at it at first, you would be intimidated. But once we get into it, I think you'll see it's actually pretty approachable. This does have to do with drawing Gaussian surfaces and a continuous charge distribution or very long charge distribution. So I think that's the intimidating part. But just dive in and see that there's lots of points here that we could easily earn. So we've got a very long, thin, non-conducting cylinder of length L, and it's centered on the y-axis. The cylinder has a uniform linear charge density of plus lambda. Point P is located on the y-axis at y equals c, where the length of this cylinder is a lot bigger than c, and that's going to be important for when we're using Gaussian surfaces, because we need that. Well, actually, we need that for part A, right? Draw an arrow to indicate the direction of the electric field at point P. If this isn't very long, and if it's not centered, we're not going to get electric field lines that are parallel to this y-axis, right? When we get closer to the edge, they're going to start bending. So we need this kind of symmetry argument, and we need this to be a lot longer than this distance here. So anyway, at point P, yeah, we will have an electric field that is straight up along the positive y-axis. Now, the next thing we're supposed to do is to describe a Gaussian surface. Describe the shape and location of that Gaussian surface that can be used to determine the electric field at point P. Well, in order to do that, we need our Gaussian surface for point P to be on our Gaussian surface. And the most appropriate one to draw would be a cylinder that's concentric with concentric with this cylinder and is not very long. I'm going to make that a length of L, and the radius will be C. Okay, and that way, for a Gaussian surface to work, you want all the electric field lines to be perpendicular to your Gaussian surface or parallel. So they'll be parallel with these faces. You won't have any flux through the circular faces, but you'll have flux through through the sides of the cylinder, and those electric field lines will be perpendicular at every point on that surface. So now we actually want to use our Gaussian surface to derive an expression for the magnitude of the electric field at point P, and our answer has to be in terms of lambda, C, L, and any physical constants as appropriate. So look, guys, they just had us draw a Gaussian surface. So we're going to have to use Gauss's law, right? So that's our next step. That's right from your formula sheet. The thing they don't say is that this Q, on your formula sheet that this is the enclosed amount of charge. Okay. Now, if there's a linear charge density of lambda, if we just multiply it by the length of that cylinder, that will be the total charge that's enclosed. Okay. Now, we said that the only surfaces of that cylinder that are going to be pierced by field lines would be the sides of it, right? And so we need the area of the sides of the cylinder, which would just be the circumference of the circle times L. Okay, so the circumference of the circle is 2 pi times the radius, which is C, and the length is L. And I'm going to substitute this for Q enclosed. You'll see the L's cancel out, and then we'll divide. Make sure you circle your answers for your grader. You could have also converted 1 over 2 pi epsilon naught to 2k, but either one would have been acceptable. Okay, now the backside wants us to draw what the acceleration and velocity vectors would be if you took a proton and you put it at point C, right? Let's just, where is that? It's on this side. If we put a proton right here, a positive charge, right, it's going to be pushed away. But the further it gets away, the weaker and weaker the electric field will be, and the smaller and smaller the net force will be. And so it will start with some maximum amount of acceleration right at point C. And that acceleration is going to get smaller and smaller and smaller. And it will actually be just the, it's got to be an inverse relationship, because the net force is going to be Q times E. Q is not going to change, but E is going to be inversely related to your distance away from your this charged cylinder. Okay, so that's going to go like that. So I did the acceleration graph first, and I thought, how is that going to translate to a velocity graph? Remember, this is velocity versus position, not velocity versus time. So you can't just say, well, the derivative of this is going to be this. Derivative with respect to time, that is. So, but what I could say is that right off the bat, I have a rapid change in velocity, and my change in velocity gets smaller and smaller and smaller the further and further away I get from the from that cylinder. Okay, I hope that was that's helpful. Now, see, this is where you can't use Gauss. We've got a distance away from this charged object that is not that much smaller than the length of it. And also it's off center, right? We need a symmetry argument. So the electric field at point P here is not going to be along the y-axis. It's going to be a little bit to the right, right? Because they're on the longer cylinder, every charge point from here and here was canceling out the x direction, or the x component of the electric field, giving us nice perpendicular, nice electric field lines that were perpendicular at that point. That's not going to happen here, right? It's there's going to be a stronger amount to the right than there is to the left, because there's more charge over here to the left. So you're going to get this electric field that's a little bit more towards the right. Okay, so it asks us, hey, can we use Gauss's law to derive an expression for the field at point P? No, we can't, right? Gauss's law requires symmetry, and with P being off center, that doesn't give us symmetry. Also, the distance is not significantly smaller than the length of the cylinder. So E will not be parallel with the y-axis, which would be perpendicular to that Gaussian surface either. Okay, lastly, and I think this is where you guys might get a little bit intimidated, but we actually don't have to do any integration. The student argues that we should use this integral, and that would give you a horizontal component and a vertical component that looks like this. All we have to do is figure out which one of these is wrong. And the good thing is that means the other one must be right. Okay, so look, our charge is distributed along the x-axis, so we have to integrate along the x-axis. So the vertical component, its expression doesn't make sense because we're looking at dy. We're breaking up those charges along the y-axis. So we need to change the dy to dx in order to integrate along the cylinder, right? Because that's where the charges are that are contributing to the electric field at point P. Okay. Also, then you have to think, okay, one of these is right, and the only thing that's different between these two is that this one has a 3/2 term and this one doesn't. Okay, and of course we already talked about the dx and the dy. So what we need to do is figure out which one's going to make sense when you actually do the integral. Okay, E in basic terms is just k times q over r squared. So we need an answer that's going to give us k times q over r, some charge over some distance squared. And that will only work if we have this 3/2 term. Because lambda is already charge per length, and you're multiplying that by length. So you do have between this term, and this term, you do have K and Q. Wow. And after we integrate, we need to end up with an R squared in the denominator. And that's only going to happen if we start from this point. I hope you guys found that useful. You definitely need to get familiar with Gauss and get used to this kind of analysis of the electric field and also electric potential, even though they didn't ask us about electric potential this time. All right, stay safe, everybody.